Many of the statistical tests that we do depend upon us being able to assert with some kind of confidence that the data set we're looking at is normally distributed. Most data sets we work with as engineers are not perfectly normally distributed, but they come pretty close as our sample size grows. We might also need to fit our data not just to the normal distribution, but to any other. So there's a technique for mapping your data to probability plots that allow us to discern which of many distributions will work best for our data. So let's talk about how to do that. We're going to create a probability plot of I number of observations. And for each of those observations, we need to know the percentile that data will be in. We'll have the observations of our data from our data set, okay, and then we want to calculate the z for that data, in this case mapping to the normal probability plot. If we were trying to map to something else, we would use some other characteristic. So we have one observation I'm going to build. You notice I'm going to build the spreadsheet to handle any number, so I want to plus 1 to that. Let's start with a very large sample. Let's say we collect 400 data elements as we go. So we'll be able to calculate a percentile for that given function by subtracting 0.5 from it. Remember to do your correction for your continuous versus discrete observations, and then divide that by the number of observations that you plan to have, and that would be the percentile of the data that will fall in that range when I explode this out to 400 observations. And then on the formulation, what you care about in terms of mapping is what would be the z factor. What's the z calculation under the normal curve that would give us an integral of 0.00125 in this case, and that's the norm's inverse. So it's an inverse functionality of the distribution. That a z of minus 3.02 would give us a probability of 0.00125. So we're going to carry that down. Okay. And then we're going to plug our data into this column and compare the two as we go. So now we just roll this down to the number of observations I plan to make, which would be 400. Okay, so I've got 400 data elements drawn with a plus 3 z to a minus 3z as I go through. And now you notice that I left the observation column empty so far, and I put it in this order. The reason I put the z to the far right is I plan to graph this data when I'm done. I'm going to want my observations to be my x-axis and my z, or my fit to this distribution, to be my y-axis. So I'm doing this practically only because of the way I know that Excel creates graphs from columns and spreadsheets. It's going to take the first column as my x and the second column as my y. Other than that, the order doesn't really matter as I go through. So what I want to do now is generate some data for that. I'm going to come over here to the Data Analysis tab, and I'm going to pick the random number generator. Now, for the sake of this example, I'm going to start by generating some normal data to show what a probability plot looks like if your data is actually normal. So I want to create one variable with 400 values using a normal distribution. Okay, that will have a mean, let's say a mean of 500 and a standard deviation of 25. It doesn't really matter what you use as your mean. What I care about is that it's a normal distribution. In the output range, I want to take my values that I generate and put them right here in column C. So if I press that value now, I get my values. So now I've got a randomly generated set of data that might have come from a customer if this were a real project, but I've actually generated it randomly. So I know it's normally distributed, but only because I generated it that way. To create the probability plot, you want to take the data you've just inserted and always sort it into ascending order. Because the Z column is in ascending order, you want your C column to be that way also. Also note the warning I'm getting from Excel. It wants to expand my sort to move the entire row. I don't want to do that. I want to move just this column within that framework. So having done that now, I can take my values and graph them. So I'm going to insert a scatter chart with just data points in it, and we'll see what that data ends up looking like. Now I'm way down there at 400. I'm actually going to cut that so I can go back to the top of my spreadsheet and paste it in. It's often easier to simply cut and repaste than to drill it in over time. So we learn in terms of our probability plots that a straight line indicates a normal fit, and this is a really straight line. So we definitely have normal data here. You might read in your text or in other sources that the straight line you're looking for in a probability plot is a 45-degree straight line. That is true if the two scales are the same, but they're often not as I go through. So don't worry about that. You're looking for a straight line. The dots at the extremes here are perfectly acceptable for a normal distribution. Remember, the normal curve goes off to infinity in both directions, but the data I generated does not. So don't be surprised if you've got some holes in the data out in the extremes that aren't a perfect fit to normal, but in fact, even those fit very, very well in terms of straight data. So the data here is very, very straight. This I would easily be able to make the assertion, looking at this graph, that the observations that I plotted were in fact normally distributed. Okay, so that's the first step. We might then want to play with some other data in our curve. Let's go back and regenerate some data. We're going to put it in the same place, but this time, instead of actually having data that's normal, let's just go with some uniform data to start. So let's just take random data between, say, 0 and 1000. I put the data in the exact same place as I go through. So I'm going to press OK. Excel will warn me that I'm overlaying the data I generated last time. That's fine with me. Now notice the data comes out very, very random in a pattern. Don't panic at that. That's because the random data has not been sorted yet. So I need to remember to take my column and sort C into ascending order. And that's when I get my curves. Here's the probability plot for a uniformly distributed data. And notice this is not a straight line. So I would not be able to assert that the data I collected in column C is normally distributed. It might fit some other curve, but I can tell you right now it's not normally distributed. If you look at the two tails, it's got a very, very heavy tail relative to the actual data. And if you interpret this properly, you would understand what's happening here. Because out here at minus 3z, as I move from minus 3 in toward the mean under the normal curve, the data accumulates very, very quickly, right? Because the curve comes up to approach the mean. In my uniformly distributed data, the data isn't increasing as I come toward the mean. It's pretty much staying flat. So what the graph is indicating is that my z is moving, so it's moving up the scale far faster than it's moving to the right, and that's why you're not getting a straight curve, because the uniform data does not increase dramatically as I shift from minus 3 to minus 1. It's just as much data in this data, my data set, at minus 1z as there is at minus 3, and that wouldn't be true if the data were normally distributed. Same at the other end. When I get out from 1 to 2 to 3, I expect to have almost no data as I get toward 3, but in fact I have just as much data out here as I would have had. So these heavy tails are an indication that the data is not normally distributed. In essence, it's showing me that I don't have the tails I would have expected out there on the data. Let's take another data set and see that one that we might map in. Suppose we had say a Poisson distribution with a lambda of maybe 10 hours and put the data in the same place. Okay, we have to, again, remember to sort your data before you interpret it. Okay, this data is reasonably straight, but it's not perfectly straight if you look. So it's a reasonable fit. So if I didn't know this was Poisson data, I might reasonably conclude that yes, the data is more or less normally distributed. It's not perfect. And if you remember back when we studied Poisson distributions and discrete distributions, it was not uncommon to approximate the Poisson distribution using the normal curve when the sample size grew. So as we had a larger sample, we ended up with a straight line, and this demonstrates that as we go through. Let's try doing the same thing again, but let's eliminate all but 25 observations here. Okay, which means I have to change my formula for the percentile. Okay, I could probably spend a few hours creating a spreadsheet that would figure that out, but don't judge this graph because this graph was from a sample of 400. So let's generate a new data set now with a Poisson of lambda 10, but let's only create 25 data values now. Okay, let's remember to sort it. Okay, you'll see that the data is all over the place. I actually got errors, so I'm not even sure what those are. Oh, I know what I did. I forgot to sort the data properly. So when I sort the data, you have to remember to do this, or it moves all the rows. See what I did? Okay. So what I did there is before the first time I sorted it, I sorted the data, but I didn't tell it not to sort the whole row. So when it mixed up all the rows, I got some weird values in some of the columns because they're all relative to each other. So I fixed that. So serendipitously, I've shown you what happens if you screw up the sort of the data. So don't do that. But notice here the data is not nearly as straight or flat as it goes through, particularly out in the extremes. And out here in the extremes is where you're most at risk of using a normal distribution if you actually have Poisson data and you don't have a large enough sample for it to become straight. So this data is curved on an arc in a way that I would not be able to claim that is normally distributed in terms of the curve. I'm okay with it being discrete. That doesn't bother me so much because it is a discrete distribution. And in fact, the fact that it's discrete like this would warn me in my data. If I didn't know it, I might realize that my data is discretely configured. But the fact that the extremes is so far off the straight line means that for this data set, I would probably draw incorrect conclusions if I used the normal curve to approximate the hidden Poisson variable. So for small sample sizes, you shouldn't be using the normal distribution for a Poisson emulation. But for very, very large sample sizes, obviously you can. So this is how you draw a probability plot for any curve. Always set up these 4 columns. Always build your percentiles the same way. And here in column D, notice I used the inverse of the normal distribution. Had I used the inverse of the gamma function or the inverse of a y-ball function, I can use the inverse of any of the functions to put the probabilities here, and I'd be doing a probability plot against that curve. No matter which probability plot you pick, no matter what you put in column D, you're always looking for that straight line. So the straight line tells you that the observational data you've put in column C is in fact matching the distribution you've put in column D. When column D is the z variable, we tend to refer to this as the normal probability plot. For anything else, we would typically just call it the probability plot, but you're looking for that straight line to be able to make that assertion.